Hi friends, good noon. Welcome to the webinar. This is Priya from Aspiration Energy. Aspiration Energy is a 8 years old organization. We are providing hot water solutions for automobile industries through solar thermal and heat pump. We provide hot water up to 120 degrees Celsius through solar thermal and up to 90 degrees through heat pump. I think you will get a brief idea about the process heating solutions after this webinar. I am going to handle the session to Professor Satyanarayanan Seshatri. Hope you will enjoy the session. Thank you, friends.
Hello. Greetings. Hope you're able to hear me. Just let me know in case my voice is not audible. So, okay, I get started with a brief overview on what we're going to talk about today and look at a few approaches that we have seen over a period of last couple of years, both in the commercial applications and in the field of research. So, the topic for today is approaches to sustainable heating. The topic for today is essentially approaches to sustainable heating, specifically looking at process heating. So you might be wondering why process heating and what is the big deal about it. So while we go through the seminar, we'll look at why we are talking and why we are interested in process heating, but at a very high level, heating typically constitutes nearly anywhere between 30 to 50%, sometimes even higher, of the energy demand of any kind of process industry. So when we say process industry, it is anything that is manufacturing oriented or chemical. I mean, essentially, it's a manufacturing oriented industry to produce something from raw material to an end product. So electricity being a primarily considered input, we also have water and heat in addition to compressed air as the other utilities. So of these, the first three, electricity, water, and air, are driven again by electricity itself. It is only heat, most of you might be aware that it is generated locally in-house. And since it is generated locally in-house, the amount of attention paid to it in terms of the efficiency of utilization, in terms of the correctness, and in terms of the potential for energy saving is often not considered or often not paid attention to. So through this webinar, I would like to bring your attention to those opportunities for improving your energy cost per unit of product that you produce by managing process heating. So we'll go through a list of a few topics, but the primary thing that where we start is essentially your boiler. So why boiler? Boiler is the place where your heat is generated. Whatever be the application, you have some kind of an energy generation system, which is a boiler. So I would like to typically bring your attention to the following scenario, what you see in the screen. So this is an example from one of the recent case studies where we have implemented an energy saving measure where the industry was consuming about 27 liters per hour of kerosene as their input fuel. And at a rate of about 87% efficiency, the kerosene can supply about 1.6 lakh kcal per hour of heat, which is a typical unit, or about 182 kilowatt, which if you can convert, because these are all energy units, you can convert from one to other. But 87% is the rated efficiency as mentioned by your boiler manufacturer. So you don't have any reason to doubt it. Of course, it is 87%. But the challenge comes in. The challenge comes in if you're utilizing it off design. For example, this efficiency and the number is valid only if your boiler is designed for the range in which you're operating. But then typically what we have seen in many applications is that the boiler efficiency is rated for a certain number or certain design capacity, but often the boiler is used at a very marginal capacity. For example, in this particular plant, the boiler was designed at about 10 lakh kcal per hour and it was used at this particular level. So what is the meaning of it? This is what happens. So essentially, to understand the meaning, you have to look at what constitutes boiler efficiency. So typically, what is called as a rated boilerplate efficiency includes the radiation losses, which is a design criteria, and the exhaust losses, essentially the heat that is let out of the chimney. And depending on the type of fuel, you can go to lower temperatures or higher temperatures. So it essentially depends on the sulfur content in your fuel. Apart from that, there are a few static losses which, if the boiler is operating under design conditions, it is very low. For example, the startup losses. And startup losses when you're cold starting the boiler. Pre and post purge losses, essentially when you are switching the boiler on and off, and especially if it's a gas-fired boiler, there is a evacuation of whatever gas is inside the boiler. And what we are particularly seeing often is the loss at high turn down. So if a boiler that is designed for a 10 lakh kcal per hour thermal output, if it's running at about 1.6 lakh kcal, efficiency significantly drops down to about less than 50% significantly. So in which case, even optimistically taking about 60% efficiency, you are losing significant amount of money. And the other challenge which you often, and some of you might say that, yes, during my running hours, I have very low load, but I do have changing loads like a batch process. So that again contributes to a significant loss in efficiency. And finally, an over-designed boiler is on standby all the time because it needs to come on whenever there is demand. So that is a huge thermal standby losses. So what is the message? A high-capacity boiler, which in case is being used at a very low capacity, efficiencies will be lower. And as a result, your cost of energy will significantly increase. And the downside in terms of maintenance of the boiler is it is constantly fluctuating. So that essentially kills the boiler. So what do we do about it? We look at how to manage loads and fluctuations. So the proven way of managing fluctuating loads, you're all familiar with electricity. The way we manage fluctuating loads electricity is sometimes by putting up a battery, especially the solar DC where the input is varying and output is also varying. You have an accumulator in between, which is an electrochemical cell in the case of electricity. And in our particular case, it can be anything. So the figure on the right that you see is an accumulator. This is now not a very widespread standard practices, but it is being promoted as an energy efficiency practice by a lot of steam boiler manufacturers. So what does it do? It ensures that your boiler is always running at its design load and it fills the steam into an accumulator. And the process is being supplied by the accumulator. And whenever there is a huge sudden demand of steam, the boiler also comes online. So you can meet over the surges in your demand, but at the same time, make sure that the boiler is operating very efficiently. And by the way, if you are able to put up an accumulator and make sure that your boiler efficiency is always at the rate of design efficiency, even at 17%, 27% gain from 60 to 87%, the previous example, we could save or avoid the loss in fuel cost by about 38.8 lakhs. So that's just simply by making sure that the boiler does not operate too below its design point. What else can we do? Of course, one of the interesting features about an accumulator, it's like it acts like a buffer. So it can act like a buffer both in terms of the supply side and also the demand side. So this allows us an interesting opportunity to integrate with renewable sources of heat like solar thermal, where you put in a solar boiler and then you couple it with an accumulator or a thermal storage system. This allows you to really make sure that your process conditions are not affected. So now you can go from solar thermal being a very finicky, infirm source to a very reliable industrial product. So in this particular slide here, what you see is an installation in one of our customer sites where we have installed a thermal storage system by the way of a hot water tank. And on the right hand side, these are the screenshot from the PLC system of that particular plant. So you can see how the primary side and the secondary side are working in tandem. So the heat is being supplied by the solar and the heat is being removed by the process, and the accumulator acts in between like a buffer. And this can be the situation. The heat primary side can be any source. It can be a boiler which is over designed but it wants to run at a high efficiency. It can be probably a heat pump, or it can also be a solar thermal system like what we have shown here. The second most important thing in terms of understanding our process heating needs is really understanding the process losses. So we are a little familiar to the losses when we say that, okay, I need to insulate my pipeline because my pipeline is at a high temperature, my ambient is at a low temperature, so I'm losing a lot of heat. But in many applications in where we are using hot water in a bath, in a big tank, like for example, this application that we are talking about, it is basically a hot water system for a pre-treatment plant. It is basically a hot water system that is used in the automotive industry. And the mass of the component that is being dipped here is about 700 kg, and the volume of the tank is provided here. And what we are required to is maintain the heat of these tanks at about 55 to 65 degrees. Now, can you guess what probably would be the biggest energy consumer here? Here you go. So basically, there are two things. For the first case where I've talked about an open top tank. So basically, you can see on your left as a schematic, which is typical of a tank, which is any kind of vat or a phosphating or a pre-treatment, any kind of tank where hot water is stored. Normally, you see, sometimes we have seen that there is no insulation, but many often there is insulation, but the top is always open. What happens? If you can see, without the insulation, the heat load required by the tank to maintain that particular temperature is about 45 degrees centigrade, whereas the actual energy uptake by the component is only about 5.8. So it is surprising. Your actual component for it to be pre-treated needs only about 5.8 kilowatt, whereas the maintaining the temperature in the tank, because from the surface there is a lot of heat loss. So essentially, understanding where the loss significantly comes from can lead a long way to go to reducing your process energy bills. So here is where understanding the process and looking at heat losses step by step helps. So just for example, in this particular case, if we are able to close the top, now you can see the heat load from the tank is significantly dropped by about 4 times. So that gives you an order of magnitude. So what next? So the major problem that we normally face when we deal with thermal systems is the reason why we are not aware of heat losses, the reason why we are not aware of how much energy, how much fuel that each unit of thermal energy costs, is because we don't really monitor the thermal system performance. Electrical energy, because it is a product, it's a utility that is metered and sent to us. We have an electric meter and we are very conscious about utilization of electrical energy. It is a standard product, it is easily metered, but thermal energy often is something that you generate by yourself. And the crudest way or the most basic method of measurement is the amount of fuel you consume. But that does not tell you, are you consuming the right amount or are you consuming much more than what you need? So then do we have any solutions at all? So the measurement of thermal energy slightly has to go back to the basic fundamentals, which essentially tells you that if there is a flow of heat, I should be able to measure the temperature and I should be able to measure the flow rate of the medium which is carrying the heat, and then I will be able to measure. So essentially it requires you to put together a small system. In terms of electricity, that system has been developed and matured and is available in the market. For thermal energy, a lot of such systems are coming up in the market, but then more and more it is becoming essential for you to install such systems on your heating lines in case you need to be able to know how much energy you are consuming. All is not so bad in terms of thermal energy, because steam is one of the primary working fluid that's being used by many people. So steam has its own meter. So this photograph in between is a picture of a steam flow meter, which is utilized to specifically tell you what is the steam consumption. So one of the advantage of measuring thermal energy is that it can give you the direct efficiency of your boiler. If you don't measure thermal energy, then you have to indirectly estimate, because like I told you, in the previous example, I am generating about 180 kilowatt, but my process demand is far less than that. My process demand is less than 120 kilowatt. So I need to really know if I'm burning fuel worth 180 kilowatt, where is the heat going? What are the various sources of heat losses so that I can improve my efficiency? So, okay, why should you monitor heat? Okay, all right, you said I'm monitoring electricity because I believe my biggest energy consumption is electrical energy. So I would answer this question by taking the example of a dairy. Dairy is a very big process industry. All of us almost have interaction with the products coming out of a dairy. So I just have put here a few products that come out of a dairy: milk, cheese, butter. There's another type of cheese, and then milk powder. So in all these cases, you can see the ratio of electrical energy required. In case of milk, it is for chilling, and in case of again milk, the thermal energy is for pasteurization, so on and so forth. So if you look at all these cases, what I come to understand is if I don't monitor heat, in fact, I'm flying blind. I'm unmonitoring about 40% of the energy my plant is consuming. So if as an energy manager or if a plant manager, tomorrow I need to cut down my energy cost by 5% or 10%, and I have done everything possible on my electricity, then I have no option. I don't know what to do. So thermal energy monitoring essentially allows you to constantly improve heat utilization process because the paybacks are quite high, and it also allows you to continuously keep track of your energy efficiency program. So if you have, for example, done an energy audit and you have done everything recommended as audit to make sure your plant is the most efficient, but then without monitoring, systems go out of it. So whatever energy efficiency gains you have achieved, it is not visible, it is not documented, and it goes down the drain. So that is why many energy auditors, including what I think, is that the reason why most of the energy audit recommendations from thermal energy audits are not installed or not implemented is because since there is no exact way to identify and attribute causes to the energy saving from thermal systems, it just goes away. So to give you a statistic, less than 10% of the thermal energy audit recommendation get implemented, and those 10% are typically common sense. Essentially, it says replace the leaking trap, replace insulation, add insulation. Some of these are very, very common methods, but there are many more energy efficiency systems like heat pumps or changing to a advanced type boiler where the savings could be of the order only 10% or 15% or maybe 20%, but then without monitoring, you would really not be able to say that I have gained or not. Number 5, what else can you do? So for example, you already have your boiler and you already are using the system, and if you are really serious about thermal energy, where are my opportunities? So one of the, again, going back to the basics, the first place to look at opportunities, go back to the sources. So when we are looking at sustainable ways of process heating, we have to really look at the utilization of our fuel. So for example, if I have a block of coal, what is the best way to utilize that block of coal so that I can get my maximum energy possible? So the most common implementation in most of the industries is to have an economizer. So what does an economizer do? It simply preheats the feed water into a boiler, and then it improves the efficiency, thereby taking off heat from the exhaust gases. So this is very useful if your fuel are of the kind where you have low sulfur, where you can cool your exhaust even down to 100 degrees C, and then you can preheat your feed water. So that, I mean, economizers can add up to 10% on your efficiency. In some applications, if your feed water is already preheated because you have done an excellent job of condensate recovery, you have recycled your hot water from all your process, you can go ahead and utilize air preheater so that you can improve your combustion efficiency. So that way, you know that for the kilogram of fuel that you're burning, you're getting the best possible energy output. But you can also look at saying, can I go towards a different kind of boiler so that I'm utilizing coal to a slightly higher potential? So where does this thought come from? For example, if you compare any kind of process boiler to the boiler typically used by, say, a thermal power plant like NTPC, the pressures that they are burning the fuel, the generating steam is significantly different. So that way, and because of which the utilization of heat available from burning of the fuel is also improved. So if you say a boiler efficiency perspective, an NTPC boiler is much more efficient as compared to your normal process boiler in terms of utilizing the coal. So how can we do that? One opportunity for us is to upgrade our process boiler to a combined heat and power system. So if you are able to fully implement it in your plant right from the beginning, you can have tremendous amount of saving on energy cost, even up to about 50 to 60%. But if most of the cases where we have been in process plant, there is already an energy infrastructure is already in place. So if we were to do small modifications and if we have the option of changing the boiler, that itself will allow me to reduce my energy cost by about 10%. So I will explain this with an example of a process boiler where the application is in a tea industry where a 6-ton boiler is about supplying 4 tons per hour of steam at 8 bar. So that is the process requirement. So now you may ask, where is the opportunity for improving and saving cost? So what if I tell you that without a significant impact or cost increase, you could have actually implemented the same process requirement using a 4 ton per hour 24 bar boiler, which is also a standard industrial boiler, and couple it to a back pressure turbine or some of those power turbines which work under back pressure and supply the 8 bar to the process, which is in this case a tea factory. So in this particular application where we had given a recommendation for one of the leading FMCG industrial houses in Chennai, the simple payback was about 1.9 years and a direct reduction in their annual energy bill is about 10%. That is considering they are using coal as a fuel. What will happen if you consider you're using furnace oil as a fuel or kerosene as a fuel? The savings could be much, much higher. So if you are able to switch to a boiler which is generating at higher pressure and have the option of running a back pressure turbine, the back pressure turbine is going to give you incidental power to your power for your local consumption, and your process is absolutely not affected. And whenever you don't have the steam requirement, you still have the grid from which you can take the power. So this essentially improves the utilization of your primary fuel, and this is what I meant by consider utilization of your heat sources. The next topic, what I want to briefly talk about is consider your cost of energy. So when I tell people that diesel and electricity almost cost the same to produce 1,000 kcal of heat, you would be disbelieving. But all you need to do is do the math yourself. Consider the calorific value of diesel, and assuming you have a reasonably good boiler and it is heating efficiently about 80%, and you look at the cost of 1,000 kcal of heat is almost identical at current cost of diesel. And most of the fossil fuels that you see here, kerosene, LPG, HFO, are not very off from electricity. So it is about time for you to consider, especially people who need heat less than 100 degrees C, seriously consider stopping burning any of these fossil fuel and switch to electricity as their primary mode. Now you may ask, how can I switch to electricity? Because electricity is more expensive than all the other fuels except diesel. That is where you should also consider, like I told in my previous slide, how you are utilizing that unit of electricity. So if you were to simply use that 1 unit of electricity in a heat pump as shown here, for the same heating requirement, now my cost has reduced by half. So now my heat pump can produce or deliver the same unit of heat for you at half the cost. Now immediately the situation changes. Now you can see that my heat pump is much more cheaper per unit cost of energy than all of it combined except my solar thermal. So if you are seriously looking at sustainable ways of process heating, some of these solutions might make sense. I mean, diesel, obviously you should stop using diesel. You are better off using electricity because at least you're avoiding local pollution. But then you should also consider eliminating some of these fired sources in-house and switch to greener sources. Specifically true if your heating requirement is less than 100 degrees C. So that gives you the previous slide here. This slide here gives you cost per unit. Cost per unit heat for various fuels, assuming your boiler runs efficiently. Now you go back to our first discussion where we began with, your boiler is not running efficiently. Here is an old chart. By the way, the numbers here are slightly off. As you can see, the cost of diesel is only 44 here. But still, if you look at it, as you decrease your boiler efficiency, you can start seeing that my solar and heat pump or any such sources become more and more expensive. So you really have to understand your cost of energy at the efficiency of utilization. And that's where things like, or studies like boiler efficiency, energy audits that give you the true picture of your boiler efficiency, and the real test of boiler efficiency is actual utilization of your thermal energy, continuous monitoring of thermal energy, all of which will tell you for the kilogram of fuel or for the liter of fuel that you burn or for kilowatt hour of fuel that you consume, what is the true value of heat that you generate. And that is where you have to all look at if you have to capture the true cost of energy into our systems. So some of the basic tenets, if you were only to take away a few simple tenets from this talk that you have, my first one would be load your boilers optimally. And if you think you have a very large boiler, there is nothing else you can do, but at least consider an accumulator where you run the boiler at full load and then shut it down or put it on standby and then supply to the process using accumulators and again run the boiler at full load to recharge the accumulator. Understand the process needs. Sustainability can come in from simply reducing losses. So some of the lowest hanging fruits of sustainability is to eliminate losses. So if you're able to eliminate losses and continuously monitor a program where you're monitoring thermal energy consumption and periodically looking for why energy consumption has increased and identify the root causes and eliminate as soon as it occurs, you are far better off in implementing your sustainability goals. Third thing is, again, related to the previous one, don't squander your efficiency gains. You have done a lot of work to achieve the gains that you have, but then without monitoring, there is no control. So do seriously look at thermal energy monitoring as an opportunity wherever possible and in whichever way possible. It is best done at the implementation stage, but it is not very difficult to implement in systems where it is currently running. It hardly takes a little bit of retrofit, but then the benefits are fairly large and it can give you a lot of perspective, not just in your energy consumption, but it can also give you a lot of perspective in the process control. Right now, you do have certain process control parameters like temperature and things like that, but the energy consumption by a process essentially tells you, is my process consuming the right amount of energy required for the process, or is it consuming more, or is it consuming less? So each of which is a case for an alarm, but then it allows you to really monitor your process and make sure that you are having the best consumption as possible. The fourth thing is consider utilization efficiency of heat sources. The big word here is exergy, which is the availability or available potential of energy. So we generally talk about energy conservation, but you would have also learned in your thermodynamics early on that energy is neither created nor destroyed. So when we really talk about energy conservation, what we are really referring to is its potential to do useful work or potential to be useful. So as we start considering my efficiency of heat sources, you're actually doing the environment a huge benefit, and you're also, it's basic economics as well, that you're improving your sustainability by utilizing the energy at its best efficiency as possible. And the last point which I want to make is switch to alternatives. We have been burning fuels for a long time, but now is a time where the alternatives have become cheaper than you think. And when I say cheaper, it is cheaper even without subsidies and any other thing. It can make attractive economic sense, and it definitely makes attractive environmental sense. So when you consider sustainability as your energy practice, and sustainability starts with everything that you do, it starts with the mindset that I have to use energy as efficiently as possible, which essentially means that switching to alternatives whenever sustainable heating becomes cheaper. And right now is a time where it is getting there, and many sustainable sources of heating are cheaper than what you think. So with that, I come to the end of my brief talk on the sustainability practices that you can do in process heating. And I am open for questions, and feel free to post any questions as you need. Thank you. So Deepa or Kavipriya there, if you're moderating, please, the floor is open for questions and comments. So if you can gather the questions and share it, I will be happy to answer. Okay, I have a question from Mr. Jaideep Malavya asking how solar thermal can be economical to heat pump. So the basic costing considered here are basically the costing considered here basically are the operational cost. So essentially what we have here is basically the cost of maintenance and operations put together. Since solar thermal does not require any auxiliary input cost, it is cheaper than heat pump. So the another way to look at it is most of this is post payback, the operation cost of various fuel post payback. So if we were to include the capital cost of solar thermal in the period of payback, the cost of solar thermal is as good as the fuel against which you are considering, and beyond the payback period, the cost drops down to the value shown here. So there is a question by Mr. Narasimha where the comment rather is that they use biomass boiler for steam and for electricity for process cooling, and the bill is about 30 lakhs per month, implying process cooling consumes high. That is typically true in some of these industries, like even in dairy industry, the biggest electricity consumption is from process cooling. So here is where your CHP or a cogeneration type system becomes a lot more attractive, where you do have incidental power output while the process heating is the primary requirement. In certain cases, you would also be able to utilize the exhaust heat or waste heat available for process cooling, but then as a mix, if you are able to consider both combined cooling, heating, and power, it becomes a lot more sustainable. Okay. So here I have a question from Mr. Arun Nagasubramanian. So the question is, can I comment on the heat losses resulting from accumulators? And the second part of the question is, what sort of batteries would you recommend? Secondly, how to monitor thermal energy losses on components such as pipes, for example? Are there monitoring devices available for this? Thanks in advance. So I will answer the first part of your question. The heat losses resulting from accumulator, it is essentially a process design. It is as much as the design that you would do for a static thermal system. So typically for a well insulated system, there are certain thumb rules or certain mathematical measurements or models that are available, which puts in the heat loss at about 100 watts per square meter of exposed area after installation. So you can estimate what is the heat loss, and it is also measured by the amount of steam that is required for makeup of the accumulator. The second question is what sort of batteries are recommended. Say, for example, in this particular case, the accumulators that we are talking about are thermal accumulators, which essentially means we are either storing it as hot water or steam accumulators. And in case of very high temperatures, like the high temperature solar thermal systems, it can be any kind of salts or thermic fluids where the temperature is stored. So it is slightly different from the lead acid or the lithium ion where you are storing charge. In this particular case, you are storing heat as the thermal as the potential that is supplied. The last part of the question is how to monitor thermal energy losses on components such as pipes, for example. Are there monitoring devices for this? That's the best way to monitor thermal energy losses of pipes is to look at two parameters. One is if you have specifically a section of pipe which is insulated, you can put in a thermocouple, say at the inlet and outlet of the pipe, and then the brief drop in temperature, if it is a single phase liquid, if it is like water, that would allow you to estimate the heat losses. The second way, if you are utilizing steam, is if you are able to measure or if you are able to estimate amount of condensate between two segments of line, that is basically the steam that has condensed without doing any kind of work, which essentially means that is the heat loss that has happened. There is a third method which is the most easiest and most useful for energy audit in a plant, is to estimate the surface temperature of the components such as pipes, where if you know the surface temperatures at a specific value and you also know what is the ambient temperature, so you could essentially back calculate and estimate what would be a potential heat loss. So that essentially allows you to measure and also collaborate with some experimental evidence as to what might be the losses. So that hope answers your question, Mr. Arun. The question from Mr. Narsima here is, how will we justify solar, thermal and heat pump here? So the way to answer this question is justify against what? So if I were to say, for example, in your case, pharma industry with the biomass boiler, the justification is a little difficult unless you consider the sustainability and the security of fuel. For example, if you say, and I have seen this happen in multiple places, that the availability of biomass sometimes becomes scarce or sometimes become difficult, and the fluctuations of prices keep changing. So in those cases, I would justify the solar against that by saying, after a period of 3 to 5 years, the heat available is at a very low cost comparable to the biomass. So that is an investment that I could make. Heat pump, on the other hand, is a primary source of heat. The solar thermal is actually a backup source, whereas heat pump is a primary source of heat. The justification comes from two fronts. If you are using electricity to run the heat pump, the heat that is being supplied to your process is one part of it, but then heat pump is like your air conditioning unit. In this particular case, you are interested in your heat output, so the cooling or the chill water output is available for you for process cooling. So in pharma industry specifically, where you have these combined needs for both heat and cooling, heat pumps make a lot of sense. The only catch here is to understand how to design your system so that both the needs are clearly satisfied, and also keep in mind that when the heat pump is running, one of the system is basically a primary circuit, meaning it is a primary source of supply. It can be either heat or chilled water. So the second one is incidental, meaning if the primary source is running, only then I have the chilled water. So, but then on a combined basis, a heat pump can be a killer choice. It can even beat your biomass fuel.
Dear participants, we have 10 more minutes to continue with the session. You may feel free to ask your questions. Satya will answer. Thank you.
while we are waiting for more questions, I just want to quickly point your attention to the screen that you see here on my right, on my left, in the graph that you see here. So essentially, if you are looking at, the world is essentially moving towards, even based on IEA, some of the reports, towards electrification of most of your utilities. So it might make sense for you to ask the question, what it means for my process or my plant. If electrification is the way to be, for example, Indian government has betted big on the automotive architecture being electrified in the next couple of years. And it also then leads to the point where the fossilized burning of fuel for heat would follow the path, especially at low temperatures. So it also begs to ask the question, what combination of the electricity and heating can I simply be managed with electricity, especially with all these renewable sources of electricity being available on the grid? So I guess this particular slide that Mr. Jaideep Alavia is asking, the slide that compares all the heat sources available. So this particular slide is slightly dated in terms of the cost of energy, but then it gives you an overall idea as to how these things work. So if there are no other questions, I think we may call it a day, and then we look forward to hearing from you. Feel free to write to me in case there is anything that you would like to know. My email address is available on the website, satya, SATYA @iitm.ac.in. So I'd be happy to talk to you either in person or through email, depending on your needs, about how we can look at your specific applications and see if it can be made into more sustainable. So like I said, this number needs a little bit more validation, especially the solar PV plus heat pump. So on an operational cost basis, if I consider solar thermal to be something where this is basically the 3.3 that is mentioned here is during the payback period. So it does seem like solar PV plus heat pump can be useful, and it can also be cheaper sometimes compared to solar thermal. So here, basically, the solar PV plus heat pump is only considering the cost of PV, assuming that I get the solar PV at 7 rupees per kilowatt hour. on the basis, on a PPA basis, rather than investing in any plant myself. In that case, solar PV plus heat pump does get cheaper.
Thank you for joining us in the webinar. Hope the webinar session was informative. We look forward to meet you in our next monthly webinar session, which would be in the first week of September. Thank you for joining.